This presentation is part of the TI-Nfocus AP Calculus video series. In this video, I'll discuss a specific concept associated with the 2019 AP Calculus exam free response question BC2, namely arc length. My name is Steve Kokoska. I'm a professor at Bloomsburg University in Pennsylvania, and I'm a former AP Calculus chief reader. Here's an outline of the information presented in this video. But first, a note of clarification. Arc length associated with a polar curve is not part of the AP Calculus curriculum. However, arc length for a curve defined parametrically is in the course syllabus. Since we can rewrite many polar equations parametrically, especially for help in sketching the curve, I can see a path to a possible AP Calculus exam question. And you know what? This is just a nice topic that involves some very cool graphs and technology. And one of the reasons I'm talking about this topic is because several students incorrectly tried to find an arc length in some of the parts of this free response question. So first, I'll actually derive the formula for the length of a polar curve. And then I'll try an application of this formula. I'll talk a little bit about the use of technology in these kinds of problems, and then I'll leave a few nice examples for you to try. Our objective here is to find the length of a polar curve described by r equal f of theta for theta between a and b. Now I'm going to derive a formula based on this theorem associated with parametric equations. If a curve C is described by the parametric equations x equal f of t, y equal g of t for t between a and b, where f prime and g prime are continuous on the interval a to b, and C is traversed exactly once as t increases from a to b, then the length of the curve C is the definite integral from a to b of the square root of dx dt squared plus dy dt squared. So we begin by rewriting or describing the polar curve parametrically. We know the relationship between rectangular coordinates and polar coordinates. So x is equal to r cosine theta and y is equal to r sine theta. And we know that r is equal to f of theta. So now we have the curve described parametrically where theta is the parameter. Looking at the formula for L, I know I need to find dx d theta and dy d theta. And I can find both of these expressions by using the product rule. Again, looking at the formula for L, consider the sum of squares of these two derivatives. Here, I squared the expressions I found on the previous slide. If I did everything correctly, I can factor dr d theta squared out of each of these terms, and sine squared plus cosine squared is 1. These two terms cancel, and factor out an r squared from each of these terms. And again, sine squared theta plus cosine squared theta is 1. So I'm left with dr d theta squared plus r squared. Let's see if we can put all of this together. So if f prime is continuous, here's a restatement of the arc length formula for a curve described parametrically in terms of theta. So using the results we just obtained, the length of a curve described by the polar equation r equal f of theta for theta between a and b is the definite integral from a to b of the square root of r squared plus dr d theta squared. Let's see if we can find the length of the cardioid described by r equal 1 minus the sine of theta. Now typically we think of a cardioid as heart-shaped. So here's a graph. Okay, I think I can see a heart here. Now note that there's some symmetry in this graph. So I could find the length of one side of the cardioid and then multiply by 2. I'll start by trying to solve this problem in a very straightforward manner. So here's r, and here's dr d theta. I use these expressions in the formula for L. So the square root of r squared plus dr d theta squared becomes this. I expanded the two squares in this step. And sine squared of theta plus cosine squared of theta is 1. And so the integral simplifies to this expression. I wonder if we can find the symbolic antiderivative here. And I'll just say yes, it's possible, and here's one way to start this. Multiply the integrand by 1 in a convenient form. Now, if you follow this through, and this is a nice problem for your AP Calculus students, you need to pay careful attention to the bounds, and I'll leave the rest of this for you. Now, I'm still going to solve this problem, but I'll revert to technology to find a solution. So here, I used the TI-Nspire to find an exact symbolic answer of 8. And that's actually a pretty amazing result. Think about this. A polar curve involving a transcendental function, and the exact length is 8. And here's a graph of the polar curve using technology. I sketched this graph using the polar equation. But I encourage you to try to sketch the curve using the parametric equations. Here's a similar example for you to try, well, at least graphically. Some would say that the cardioid that we just looked at isn't really a very good sketch of a traditional heart shape. So consider the graph of the polar curve described by this equation. First, sketch a graph of this polar equation. And then find the length of the curve described by this polar equation. And finally, here are a few more examples for you to try. Find the length of the curve described by each polar equation. And you might also try to sketch each polar curve, both in polar form and defined parametrically. I hope this video provides some insight into arc length of curves described by a polar equation, and provides a few AP Calculus, well, at least calculus-type problems. And just a reminder, there are lots of valuable resources on the TI website. There's material there involving technology and calculus, classroom activities, and lots of calculator tips and tricks for test success.